Okay, this is the P4 paper from January 2024. It's question number 7, and as we can see, this is an integration question, in particular integration using substitution. And if we look at the second part, we can see this is a volume of revolution. But let's have a look at this part A because it looks particularly nasty. It says, using the substitution u equals 4x plus 2 sine 2x, show that that integral is equal to that answer. Right, okay, if we're going to do this, let's write out the question first of all. So we've got the integral between pi over 2 and 0 of e to the 4x plus 2 sine 2x multiplied by cos squared x dx. And what we're trying to do is to show that it's equal to an 8th e to the 2 pi minus 1, but we'll worry about all that later. Okay, it looks quite complicated, but let's just break it down into the nice simple parts that we have for any integration by substitution. They've told me that the substitution is u equals to that part there. So I know I'm going to get e to the u, which means it's the cos squared x that's going to cause me a problem, and it's also my limits that are going to cause me a problem. So whenever I'm explaining to my students, I always say, start out and actually focus on the dx part here. When I do that dx, I'm hoping in this question that that'll probably get rid of that cos squared, but even if it doesn't, getting dx sorted out first of all will then show me what else I've got to do. So they've told me that the substitution is u equals 4x plus 2 sine 2x. So first thing we've got to do is to differentiate that. Differential of 4x is no problem at all. For differential of 2 sine 2x at this stage of P4, this really shouldn't be causing you any problems. If this does, you need to go back and look at a little bit more work on that before you carry on with this video. So I've got du by dx is equal to 4 plus 4 cos 2x, and I really was hoping it had something to do with cos squared, but because I've revised hard enough, I actually know that there is a link. Cos 2x is 2 cos squared x minus 1. So if I've got 4 plus 4 cos 2x, then I'm now going to see what this all simplifies out to. So du by dx is going to be 4 plus 4 lots of 2 cos squared x minus 1, which is then 4 plus 8 cos squared x minus 4. Oh, brilliant. Yeah, that's exactly what I was hoping to get. It's got a cos squared x in there. And so what I can now say is that dx is equal to du all divided by 8 cos squared x. So when I'm trying to sort out this, filling everything in here, the cos squared dx, that's going to, or the cos squared dx, is going to disappear in terms of being with the du there. I always, at the same stage up here, would sort out my limits. So we said one of my limits was x equals pi over 2, but u is equal to 4x, so 4 pi over 2 plus 2 sine 2 lots of that, so 2 sine pi that's going to be. That all works out to be 2 pi. Brilliant. And then for x equals 0, u will be 4 lots of 0 plus 2 sine 0. And again, that's just going to work out to be equal to 0. So I've got my limits now. I'm working my way through the function that I've got to do. So let's see what we were trying to get. We had the integral between pi over 2 and 0 of e to the 4x plus 2 sine 2x cos squared x dx, and we can now replace. We can now say the limits have changed to 2 pi and 0, e to the u, and cos squared x is just going to work out to be, well, rather cos squared x dx is going to work out to be du over 8. And so what that then tidies up to is an 8th, the integral of e to the u du between 2 pi and 0. well, the integral of e to the u is just e to the u. Oops. So it's just going to be e to the u between 2 pi and 0, which in other words will be an 8th e to the 2 pi minus e to the 0 and e to, well, in fact, let's do it slowly, simply because we're showing all the working out here. E to the 2 pi minus 1 there, and brilliantly, that is what we were trying to do in the first part. So we've managed to prove that first part. Second part says this area is going to be rotated about the x-axis. We're going to have this sort of volume of revolution here. We're going to be rotating about the x-axis, and it says find the volume of the solid formed. Just have a quick look at that. It's just straightforward. It isn't anything too complicated, but it is worth just having a quick look to make sure. The integral of this one, the volume, is just going to be the integral between 0 and pi over 2, they were the limits, of pi y squared dx. Okay, so if we do that, then that's, let's take pi out, integral between pi over 2 and 0, and we're going to get 6e to the 2x plus sine 2x cos x. It's that squared dx. Just show you, sorry, because I rushed through that bit there. Yeah, y has got that equation, so it's pi y squared with that one. So I'm expecting this to be nice. So actually, as we do that, then we can say, okay, well, let's take the 36. 6 squared is 36, so it's 36 pi, integral between pi over 2 and 0. But then e to the 2x plus sine 2x, e to the 2x plus sine 2x. If we're squaring that, what you do is you're basically saying e to the 2x plus sine 2x again. You're just multiplying those two things together, and when you multiply those two things together, you add the powers. If you add the powers, we're going to get 4x, and we're going to get 2 sine 2x. Now, that's actually what the question was, so that works out, and I'm sort of expecting that to work out like that. That's going to be e to the 4x plus 2 sine 2x, and obviously cos x squared is just cos squared x dx, and the whole point about doing that then was that this bit here now, we already know what the answer to that is. So this is now 36 pi, we already had an 1/8 of e to the 2 pi minus 1. Doesn't always work out as to being as easy as that. It could have been that we needed to do something with our original integral, but here, no, it just works out to be that. Tidy it up to, that's 9 pi over 2, but then e to the 2 pi minus 1. And that's a lovely, neat answer to such a complicated function in the first place. The examiner's done really well there to give us that all dropping out quite nicely. So I'm pretty convinced that I've got that right, simply because it all worked out so neatly. Okay, hopefully that one makes sense to everyone.